Some stories begin with "once upon a time." This one begins near an ending, yet not with cruelty as entertainment, and not with panic as a lesson. It begins with humility. The non-avian dinosaurs, those great Mesozoic lineages that fascinate children and scholars alike, did not vanish because they failed at being alive. They vanished because the Earth and the sky above it can change faster than even magnificent bodies can adapt. That truth is not meant to frighten you. It is meant to connect you to deep time, to the fragility and resilience of life, and to the people who read stone the way others read poetry. In this episode, we will move slowly, as a good documentary should. We will look at what fossils record, what chemistry whispers from thin clay layers, what craters hide beneath waves, and what volcanoes piled across millennia. We will also look at the human side of science, how ideas clash and converge, how certainty grows in some places and modesty in others. And we will look outward to meteoroids, meteorites, asteroids, and comets, not as movie villains, but as real objects with real orbits, studied by people who love the future enough to measure risk with care. Picture the late Cretaceous not as a postcard monster parade, but as a functioning planet: forests, coastlines, seasons, food webs. Tyrannosaurus and Triceratops are famous residents of North American formations like parts of the Hell Creek region, yet they were not universal rulers in every habitat worldwide. Dinosaurs lived on continents shaped differently from today's map, in climates that varied from humid lowlands to drier interiors, alongside mammals and birds and insects and countless marine species in warm, shallow seas. When scientists speak of the extinction, they mean a geologically sudden disappearance of many forms of life, especially among certain groups. It was not the only mass extinction Earth has known, but it is one of the best studied, partly because it is recent in geologic terms and partly because it left a distinctive signature in rocks around the world. That signature is where our story sharpens from panorama to detective work. Geologists mark the end of the Cretaceous and the beginning of the Paleogene with the abbreviation KPG. The K comes from Kreide, German for chalk, a nod to Cretaceous limestones. PG stands for Paleogene. In the field, the boundary can appear as a thin band of clay or a subtle shift in fossils, a line in a cliff face that separates worlds. Below that line, in many places, you find a suite of late Cretaceous fossils. Above it, the large non-avian dinosaur fossils disappear from the record, along with dramatic changes in marine plankton. The boundary is not always equally clear at every site. Geology is patchy, erosion is uneven, but where it is preserved, it behaves like a shutter clicking on an ancient camera, before, after. In the late 1970s and early 1980s, Walter Alvarez, Luis Alvarez, Frank Asaro, and Helen Michel helped change how Earth scientists imagined catastrophic change. They studied an Italian limestone section at Gubbio, where the KPG boundary appeared as a thin clay layer. Above and below, they could measure elements in the rock. In that clay, they found an enrichment of iridium, an element rare in Earth's crust, but more common in certain extraterrestrial materials. The hypothesis was bold in the best scientific sense. Perhaps a large asteroid or comet struck Earth, vaporized rock, spread fine dust globally, and left a chemical fingerprint in the sediment. Critics responded as science requires, demanding alternative explanations, such as volcanic sourcing or unusual ocean chemistry. Over years, the extraterrestrial interpretation gained strength not from one paper's charisma, but from a growing network of independent lines of evidence. Earth rocks can tell stories of violence without showing us violence. Shocked quartz grains, marked by microscopic patterns consistent with intense shock, appear in KP boundary sediments far from any single local volcano. Microscopic spherules and melt droplets, associated with rapid heating and quenching, join a chorus of materials that look less like ordinary slow geology and more like a sudden, high-energy event distributed widely. These details matter because they help separate something enormous happened fast from the rock record is misleading us. Science is often a contest between parsimony and caution. The boundary layer became, for many researchers, a case where multiple independent mineralogical and chemical clues pointed the same direction, while still inviting careful work on preservation and transport. A crater's size can exceed a city, yet still escape casual notice, especially if buried beneath younger sediments and coastal waters. The Chicxulub structure, centered near Mexico's Yucatan Peninsula, emerged through geophysical surveys and drilling as a striking candidate for an impact basin roughly 180 kilometers across, linked to the end Cretaceous moment. Drilling programs have recovered rocks that speak of melt, breccia, and the chaotic aftermath of a tremendous collision. Chicxulub does not solve every mystery of life's history, but it gives catastrophe a geography. It turns an abstract something from space into a place you can map, an anchor for models of tsunamis, earthquakes, wildfires, and climate perturbations. It also reminds us how much Earth still hides beneath soil and sea, waiting for patient instruments. Expeditions have pulled cores through melt rock and peak ring materials, translating kilometers of depth into timelines of minutes and hours at the moment of impact, then into millions of years of burial. Each core segment is handled like evidence in a careful trial, described, photographed, analyzed, debated. If you love museums, imagine a different kind of exhibit, a refrigerated room, a microscope, and a person whispering, "This grain crossed the sky before it fell back to Earth." When a fast-moving cosmic body hits Earth, enormous kinetic energy becomes heat, light, shock waves, and ejected debris. Models describe a fireball, a plume of vaporized and molten rock, and a spreading curtain of ejecta. Near the impact, effects are extreme. Far away, the planet still feels consequences through atmospheric dust, climate shifts, and ocean chemistry changes. Researchers sometimes translate kinetic energy into multiples of everyday reference events, always noting that such comparisons are imperfect and that impact physics is its own field. The honest goal is proportion, enough to respect the event, never enough to glorify destruction. We do not need graphic imagery to understand scale. We can compare energies to earthquakes and volcanic eruptions in careful terms, knowing comparisons are always imperfect. The point is not to numb you with numbers, but to convey a scientific fact with calm clarity. This was an event capable of altering the thin film of atmosphere and ocean on which life depends. One widely discussed consequence is a prolonged reduction of sunlight reaching the surface, sometimes described with metaphors like impact winter. Fine dust and sulfate aerosols can scatter and block light. Photosynthesis suffers. Food webs, which are networks of dependence, can unravel not only from immediate heat and blast effects in some regions, but from the slower starvation of ecosystems as primary production collapses or shifts. Oceans feel this too. Plankton communities changed sharply at the boundary in many records. Because the ocean is interconnected, surface waters, nutrients, oxygen, acidity, shocks can cascade. Scientists debate timing and magnitude region by region, which is healthy. The fossil record is not a single video clip. It is thousands of partial frames stitched by specialists who disagree in productive ways. Some sedimentary sequences include hints of enormous waves and disturbed coastal sands, possible signatures of tsunamis, or related seiche-like oscillations in enclosed basins, interpreted with local geology in mind. A child need not visualize destruction to grasp the scientific claim. Water moves when the solid earth shudders, and those movements can leave distinctive layers for geologists to find later, like fingerprints. Research explores wildfire soot in boundary sections, suggesting widespread burning of vegetation in some scenarios. Models and geochemical evidence also explore acid rain effects and ocean acidification linked to vaporized target rock and subsequent geochemistry. None of these mechanisms needs to be exaggerated to be serious. They are ways Earth's systems couple: sky, sea, land, life. When we speak of stress, we can feel empathy for ancient creatures without pretending we can narrate individual suffering. We speak of populations, species, and ecosystems. The scales science can actually see. That restraint is not coldness, it is honesty. Non-avian dinosaurs are the popular face of the extinction, yet they were part of a broader pattern of loss that included pterosaurs and many marine reptile groups, along with severe disruptions among plankton and other marine life. Birds, avian dinosaurs, survived, though not every bird, lineage. Mammals persisted through groups that were often small-bodied generalists, even if the mammal story afterward is one of diversification in a changed world. Patterns invite questions. Why do some lines survive? Body size, diet flexibility, habitat buffering, reproductive speed, hibernation-like strategies, and sheer luck all enter modern discussions. The answer is rarely one trait, it is a braid. Crocodiliforms and turtles, among other groups, offer examples of lineages that made it across the boundary in forms recognizable to broad taxonomy, though species-level detail varies by record. Insects, plants, and fish tell complementary stories, some lineages disrupted sharply, others continuing with change rather than total erasure. When we say extinction, we mean statistical loss across the tree of life, not identical fate for every twig. In some terrestrial sections, paleontologists describe a fern spike, a temporary rise in fern spores relative to other plant spores and pollen shortly after the boundary. Ferns can be pioneer plants after disturbance. The spike is not a romance novel about hope, it is an ecological signal that suggests rapid landscape disruption followed by early colonizers. Still, for a family listening, it can be a gentle image, life looking for footing. Not every scientist has placed a cosmic impact at the center of the causal story, and even those who do often acknowledge another enormous influence, the Deccan Traps flood basalt province in what is now India. These eruptions produced vast volumes of lava over extended intervals, releasing gases that can affect climate and ocean chemistry. Debate continues about the precise tempo of eruptions relative to the KPG boundary and how much they stressed global systems before, during, and after the impact. Some models emphasize synergy. A world already pushed by volcanism might be more vulnerable to a sudden extraterrestrial shock. Others stress the primacy of one mechanism in the final blow. What deserves your trust is not a slogan, but the process, dating improvements, improved geochemistry, and integrated Earth system models. High-precision dating using radioactive decay schemes in volcanic ash beds, applied with painstaking lab work, helps align Deccan lava flows, Chicxulub melt products, and boundary sections worldwide. A few 100,000 years can sound like a rounding error to a child, but to a geochronologist it is the difference between before, during, and after, and therefore between models that compete in serious journals. Healthy science rarely ends with one cause always. It ends with weighted evidence. The KP story, as told in conferences and textbooks today, often sounds like this. A large impact is very well supported as a major driver of global environmental collapse at that time. Deccan volcanism and longer-term climate trends may have mattered as background or amplifiers. Regional variation was real. Survival was selective. This complexity is not a weakness in the story, it is maturity. The universe is not obliged to give us a tidy villain. It gives us a planet with interacting parts. Historically, people proposed many ideas: gradual climate change alone, sea level retreat, disease spread across species, supernova radiation, and more. Some ideas faded because predictions failed. Others contained grains of truth. Climate and sea level do matter in Earth history, even if they could not explain the full global signature. Science's past mistakes are not shameful when they are corrected by evidence. They are the staircase. When we teach students about extinction, we can teach them how to change their minds, a human skill as important as any fact. Sites in North America, Europe, and elsewhere bracket the boundary with bones, leaves, and microfossils. The Hell Creek Formation and related rocks are famous for dinosaur fossils below the boundary and different biotas above. Interpretations must handle preservation bias. Not everything fossilizes, and not every ecosystem is equally represented. Occasionally, exceptionally preserved sites capture moments near the event with stunning detail: sedimentary structures, ejecta spherules, and organisms buried quickly. Excitement is natural, but so is caution. Each site is a window, not the whole house. Scientists test claims with repeatability, independent teams, and careful stratigraphy, the discipline of reading layers in order. The ejecta layer itself, spherules formed from droplets of rock that cooled as they flew, can appear thousands of kilometers from Chicxulub, a sobering measure of how thoroughly a planet can be wrapped in its own pulverized crust. Touching that idea does not require fear, it requires perspective. We live on a sphere with a thin shell of habitability, and geology is the memory of how easily that shell can be perturbed. Marine microfossils such as foraminifera provide high-resolution timelines in many deep-sea cores. Across the boundary, plankton communities can change drastically on short geologic timescales. These shifts matter for understanding ocean productivity and carbon cycles. They also show how the extinction was not only a dinosaur story, it was a planetary story, written in calcareous shells smaller than a grain of sand. If you feel wonder here, that is appropriate. The smallest things can be the clearest clocks. Words matter. A meteoroid is a small, rocky or metallic body in space. When it enters Earth's atmosphere and glows, we call the phenomenon a meteor. If a fragment reaches the ground, it becomes a meteorite. Asteroids are generally rocky bodies, often irregular, orbiting the Sun, most in the asteroid belt between Mars and Jupiter, though near-Earth asteroids have orbits that approach Earth. Comets are icy bodies that develop glowing comae and tails when near the Sun. They can also pose impact hazards, though statistics and orbits differ from those of many asteroids. Earth's history includes abundant small impacts and rare large ones. Chicxulub class events are uncommon on human timescales, but not negligible on geologic timescopes. That is why astronomers survey the sky, catalogue orbits, estimate sizes, and discuss mitigation concepts, not from Hollywood panic, but from engineering and probability. Smaller impacts remind us the solar system is not empty. The 1908 Tunguska airburst and the 2013 Chelyabinsk meteor injured people indirectly, chiefly through shock waves and flying glass, yet they also produced a wealth of scientific data. They are not duplicates of Chicxulub, but they are real-world lessons that rocks arrive, atmospheres matter, and preparedness can be humane. When families worry, adults can translate worry into wonder. We track objects because we can, because cooperation exists, because telescopes are tools of care. Asteroid sizes and compositions influence risk. A dense iron body behaves differently than a loose rubble pile. A comet's volatile content changes how it interacts with atmosphere. Uncertainties are large, which is exactly why surveys emphasize discovery. You cannot plan well for what you have not measured. The Torino scale, used to communicate hazard levels, exists partly to prevent rumor from replacing mathematics. Programs such as NASA's planetary defense efforts and international collaborations work to discover and characterize near-Earth objects. Telescopes measure positions over time, refining orbits. When a hazard is identified, scientists discuss deflection strategies as long-led possibilities, again, a field where calm precision matters more than adrenaline. Kinetic impactors, gravity tractors, and other concepts live in technical papers long before they live in spacecraft blueprints. The common theme is lead time. The earlier an object is found, the gentler the nudge required to change a future intersection. That is a hopeful sentence, and it is also a disciplined one. It says, vigilance is not superstition, it is engineering ethics applied to a big sky. None of this is meant to steal sleep from children. It is meant to show that caring about the future can look like careful measurement, a profoundly loving act. We stop where you asked at fossils and the stories they tell, and at the human effort to read the sky honestly. The KP boundary is a page in Earth's book. It records loss and survival together. It records an object from space, a planet's response, and the slow rebuilding of forests and seas. It also records something about us, that we are the kind of species who tries to understand, who builds museums and instruments, who teaches with respect, and who can choose to speak about danger without delighting in fear. May you carry away a quiet gratitude for birds, for scientists, for teachers, and for the patience of stone. And may you remember that the past is not only an ending, it is also permission to protect what is fragile, to wonder what is true, and to keep learning gently for as long as the earth will let us listen.